Welcome back to the last unit. So the first thing they introduce in this section is reversible reactions, where a reaction can go in both directions, and it generally will find some kind of balance where it has some of its right side stuff and some of its left side stuff, products and reactants, at the same time. Your ingredients don't all get used up. And so we measure what these reactions want to do by calculating something called a reaction quotient, which is the ratio of the products to the reactants. That is the concentrations of the products and the reactants. So given a reaction like this, the Q for quotient, we'll start out with the obvious part. We do each of the concentrations of each of the products. We're going to have the concentration of nitrogen times the concentration of steam. Those are the two products. Over, and on the bottom we put our reactants, ammonia and oxygen. But wait, there's more. Each of these coefficients that appears in the reaction turns into a power when you write the reaction quotient. So if we have two N2s, that means here we write N2 to the second power. 6 steam, power of 6. 4 ammonia, power of 4. 3 oxygen, power of 3. So we don't have those concentrations here, so we can't calculate this. For now, we just want you to set up the expression. Later, we'll ask you to write this and we'll say, write the equilibrium expression for the combustion of ammonia. And you'll write this. And then we'll show you how to find these numbers and manipulate them and find out hopefully interesting stuff. Okay, so let's knock off some reps of this. It's generally not too bad. Except in these reactions, there are some things whose concentrations are not counted, to wit, solids. The concentration of a solid is hard to compute because it's ultra high inside pieces of the solid and basically zero outside. So we sidestep that complication by not counting them at all. When you have solids in a reaction, just pretend they aren't there and count the other stuff. Oh, this is solid too. So in the second reaction, we end up having Q equals, there are no products counted in the reaction quotient, so you just write a 1 there because we can't have 0 over our reactants. And on the bottom, we put the concentration of ammonia and coefficient of 2 becomes a power of 2. Fair enough. If you ever have all solids on the left, then those wouldn't be counted and your denominator would be a 1. Okay, let's see if they can get us with anything else. Solid, gas, gas. All right, so again, solid, don't count it. Silver, don't count it. For C, our reaction quotient is going to be carbon dioxide, power 2, oxygen. You can write a power of 1 if you want to, but it's not necessary, it's assumed. And as there are no reactants, you could put this whole thing over 1 if you like. But of course, dividing by 1 is kind of a mathematical null, so if you leave it out, it won't hurt anything. And last one, oh, they're still trying to get us with the solids. Sodium nitrate is a product, NaNO3. Coefficient of 1 means first power. And downstairs we have sodium chloride and silver nitrate. And if the coefficients are all 1, then these powers are all 1, which means writing them is optional. You could leave it like this or throw in 1s if that makes you happy. Good.